In this video, I introduce a weak sleep algorithm for unsupervised networks. Supervised learning requires labeled training data and specifies some method to communicate error information to all the connections. Weak sleep algorithm avoids these requirements. However, other goals are required to force the hidden units to extract the underlying structure. For example, learning representations and being able to reconstruct the input. Our task is to minimize the description length to capture the underlying regularities in input. The input is not used as the ground truth to define loss. Instead, helps updating model parameters. Weak sleep algorithm consists of two phases. In the weak phase, we open eyes and take the input in to generate representations. In the sleep phase, we close the eyes and generate a new distribution from the representations. The top-down procedure is a generative model, and the bottom-up procedure is a recognition model. Weak sleep algorithm learns representations of input data, namely minimizes the description length of representations so that the minimum description length is used to reconstruct the input data completely. Suppose that neurons are stochastic binary units with values 1 or 0. State of unit V is indicated as V, and the state probability is defined as this formulation, where BV is the bias of the unit V, and WUV is weight from unit U to unit V. The description length of a binary state of unit J is defined as the sum of two terms, where SJ alpha is binary state of the unit J in the total representation alpha for input, and the PJ alpha is the probability that the unit J is on. The description length C for input vector D using the total representation alpha is a cluster C of describing all the hidden states in all the hidden layers plus the cluster C of describing the input vector given the hidden state. We further rewrite the first term as a loss over all the hidden units, and the second term as a loss over input given hidden state, where L is index over the L layers of hidden units, and I is index over the input units. In the weak phase, the recognition weight determines the conditional probability distribution Q over the total representations. If the recognition weights are fixed, we modify the generative weights to minimize the expected cost of describing the input vector using stochastic total representation. After using the recognition weights to choose a total representation alpha, the generative weights are updated using derivative of C to reconstruct the input. To update the recognition weights WJK, we turn off the recognition weights and drive all units using the generative weights from the topmost hidden layer to the input units. Because the units are stochastic, we repeat this procedure to produce many different fantasy vectors on the input units. Having produced the fantasy, we adjust the recognition weights to maximize the log probability of recovering the hidden activities that caused the fantasy here, where gamma specifies the states of the hidden units and the input units for particular fantasy. K gamma is a probability that the unit key is on, and S G gamma is a binary activities in the layer below. We train the model until the recognition with WJK and the generative with WKJ reach convergence. For more details, please check with these references. Thank you. Bye.